In the previous video, we talked about the zeroth law of thermodynamics, which stated that if two systems are in thermal equilibrium with a third system, then they must be in thermal equilibrium with each other. If the third system we choose is a thermometer, it has very few degrees of freedom compared to the system of interest, whose temperature we would like to measure. And it has to have a thermometric parameter theta, which varies appreciably due to heat absorption or loss. So looking at some examples of thermometers, first of all we have a mercury thermometer. You can see here it's the column of the mercury in the capillary inside this tube that is measuring the temperature. So basically you can see here that we are looking at the change in the height of this column. So we have height of the column that varies as a function of temperature. So for the case of mercury thermometer, we have the height of the column that varies as a function of temperature. So theta, the thermometric parameter, is the height of the column, mercury column. On the other hand, we can have a constant volume gas thermometer. Here you can see that the mercury level is fixed at a certain position here. So that is at this level. And then we have the other side of the tube under vacuum. And as a result of changes in the pressure of the gas that varies with temperature, we're going to see a change in the level difference on the right-hand side of the constant volume gas thermometer. So how much is the pressure of the gas? That we can measure by looking at this extra distance the mercury travels inside the column. So we're looking at this part, and so we can determine the pressure of the gas to be equal to the mass of the mercury multiplied by the gravitational acceleration divided by the perpendicular area. What is the perpendicular area? It is basically the cross-sectional area of this tube, that is area A. So we can see that this is going to be equal to multiplying it with the height, mass of the mercury, G, the height of the column on the right hand side, H, divided by perpendicular cross-sectional area times H, that's volume. So we obtain here mass of the mercury divided by its volume, its density, times GH. Therefore, the pressure of the gas that varies with temperature will be reflected in H varying with temperature. So this is going to be pressure of the gas determined to be rho mercury GH. Therefore, for this thermometer, the thermometric parameter theta is the gas pressure. Why does the gas pressure change with temperature? Because we have ideal gas law, PV is equal to nRT. If you have a constant volume, P is proportional to temperature at constant volume and constant number of moles of gas. So basically we can use the ideal gas law in order to see the temperature dependence. So it should be a linear dependence on temperature. Another example we can talk about is the constant pressure gas thermometer. Now here we measure the height of the mercury level on the right hand side, and we keep the pressure constant, so the level difference is kept constant. So pressure of the gas is fixed. It is equal to rho mercury GH. So H is this height of the column on the right hand side here. And therefore, since we have pressure of the gas multiplied by the volume of the gas equals to nRT, under constant pressure, volume of the gas is proportional to temperature at constant pressure. So we're going to see that V is equal to nRT divided by rho mercury GH, which so this H is fixed right now. Therefore, we're going to have the volume of the gas varying with temperature. So theta is the gas volume. How do we detect changes in volume of the gas? By measuring the height of the mercury level on the left hand side here. We can give other examples. We have, for example, the resistive thermometer. This could be the commonly used resistive thermometer is coil of platinum wire. Because the resistance is a function of temperature at constant pressure, ambient pressure basically, we're going to have theta, the thermometric parameter is the resistance. How does resistance change as a function of temperature? If you're wondering, we learned this in solid state physics. Resistance as a function of temperature for metals varies as this curve. So it is basically proportional to temperature, but then it saturates at low temperatures. This is for, let me emphasize that this is the behavior for metals. So like the platinum coil wire, we will see a linear dependence on temperature. Another example is paramagnetic thermometer. The magnetic susceptibility, chi, is defined as magnetization divided by the applied magnetic field. So this is an important parameter in determining the magnetic characteristics. Magnetic susceptibility, it tells us the response of the magnetic moments to the external magnetic field. So here this M, capital M, is called magnetization. It is total moment M divided by V. So let's say M total divided by V. This is magnetization, which is equal to M total is total magnetic moment, and V is volume. So you have H, the applied magnetic field, and therefore here we have the magnetic susceptibility as a function of temperature is given by Curie-Weiss law. It's a sum constant divided by T minus Tc. This is known as Curie-Weiss law. If you study spintronics, for example, you will learn that this is the variation of magnetic susceptibility with temperature. So we can use this relationship in order to to get the temperature of the system by measuring magnetic susceptibility, and that can be done by using techniques like squid or vibrating specimen magnetometry, etc. So in this thermometer we have theta, the thermometric parameter, is the magnetic susceptibility. So in all of these devices, we need a thermometric parameter. It's some property of the system that varies in a well-defined manner with temperature. So in the case of mercury thermometer, it's straightforward. We can use the column height. It's actually the volume of the mercury, liquid mercury, that's changing because the area, cross-sectional area, is fixed. It's the height that measures the temperature. So height is the thermometric parameter. For a constant volume gas thermometer, it's the pressure that varies with temperature, which can be detected by changes in the height of the mercury level on the right hand side. For constant pressure gas thermometer, it's the volume of the gas that changes with temperature, which is given by the ideal gas law here. And we can detect the temperature changes by measuring the height of the mercury level on the side where the gas is occupying some volume. And further examples, we have resistive thermometer. Metals have a very nice temperature dependence for their resistance. For ordinary temperatures, it's usually varying as linearly with temperature. So we can use, for example, a coil of platinum wire. We apply a constant voltage, detect variations in current, so we can determine the resistance from V over I, and basically the voltage is fixed. So under fixed voltage we have the current that will change as a function of temperature, which will give us the resistance change as a function of temperature. So thermometric parameter is the resistance. In the paramagnetic thermometer, we can use magnetic susceptibility, total magnetic moment per volume, magnetization, divided by the applied magnetic field gives us magnetic susceptibility, and according to Curie-Weiss law, it's a constant divided by T minus the Curie temperature, which is a threshold temperature where we see a phase transition. So we can detect the magnetic susceptibility using advanced magnetic characterization techniques like VSM, vibrating specimen magnetometry, or squid measurements. And so we can take magnetic hysteresis loops and determine the slope, which is m divided by h, and this is going to give us as a reading the thermometric parameter theta. Magnetic susceptibility measures the temperature of the system of interest.